All right, kiddos. Hope you're doing well. Good chat today in class. Let's continue that anytime. Um, I want to show you how to use these ideas, sine, cosine, tangent in particular, to find missing sides or angles of a right triangle. So this is called solving right triangle. So let's first consider the unit circle, right? And because of triangle similarity, if I kind of take the same triangle and then I escape the unit circle, and let's just make it larger. So bam, bam, bam. And so there's my right angle here. And let's assume that same angle theta is preserved. Actually, let's not assume that has to happen. So that's required. So we'll make it look similar. And so now what I've done is by preserving the same angle-angle relationship, if I call this guy angle in here theta, let me see if I get that theta sign, then I can kind of create two similar triangles, right? And by doing so, since these two triangles are similar by angle, theta, theta, angle, 90, 90, I know that the corresponding sides have to be proportional, right? So let's kind of go there. Now, we have to name some sides, so what we do is we can call that A, the point, we can call that point B, and we can call that point C. Those are the three vertices of our triangle. And basically what we do is we say, okay, the side across from angle A, we call little a, right? Side A, right? So the little a is the side, and the big A is the angle across from it. In the same way, sorry, I'm trying to fix this. If this is angle B, the right angle, then the side across from that I'll call B, little b. And if this is angle C, then the side across from that I'll call little c. Okay? Fair enough? And so this is just a way to kind of think about or frame a general right triangle. Okay? Now, I'm going to take it a step further. I'm going to get rid of the A's, the B's, and the C's. And I'm going to just kind of look out at this triangle from this reference angle, okay, theta. And so if that reference angle theta is the angle that I'm looking out into this triangle from, then we can name each of the three sides relative to this reference angle. So the side opposite the angle theta is called O for opposite. O for opposite, right? The side underneath, quote unquote, the side theta, my reference angle, is called the adjacent side, A for adjacent. And the hypotenuse is and always will be the side across from 90 if it's a right triangle. So that's the hypotenuse. I call it H for hypotenuse, right? So what I can establish is because these two triangles are similar by angle, then what happens is the ratio of sine over 1 is equal to O over H, right? So sine over 1 equals O over H. So therefore, we can get sine of theta over 1, which is just sine of theta, is equal to the ratio of O over H. So sine of theta equals the ratio of the opposite to the hypotenuse side, given that theta is my reference angle. In a similar way, I can say the cosine over 1 is equal to the ratio of A over H. Therefore, the cosine of theta is equal to the ratio of, oops, sorry about that, cosine of theta equals a ratio of A adjacent over hypotenuse relative to this reference angle. Cosine over 1 equals A over H, right? And in a similar fashion, the tangent of theta, remember, tangent is sine over cosine, so therefore jump over to this side, it's opposite over adjacent, right? So the tangent of theta, see if I can get this theta right the first time, almost, yep, is equal to the ratio of the opposite to adjacent side, right? So these three trigonometric equations we kind of generalize, and we call that SohCahToa, right? So, sine is over H, cosine is A over H, toa, tangent is over A, right? So that's just a kind of way to remember. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, okay? So we jumped out of the unit circle to any right triangle. Okay, so we can use this to solve right triangles. So for example, what if I had this particular right triangle here? I'll just throw it up, assume that's the right angle. And this side is 3, And let's see that reference angle here, which I can use either the non-right reference angles, but let's say that side right here, the angle rather is, I don't know, 42 degrees. Okay? Right? So let's say solve that right triangle. So I can find either the adjacent side or I can find the hypotenuse. Right? So to do so, I'm going to first determine what I want to find. And so if this is my reference angle, then the side called 3 is the opposite side. And the side, quote-unquote, underneath it, at least in this case, is called the adjacent. And this side, therefore, is the hypotenuse. Across from 90, that's 90. Okay? So what I want to do is first establish, okay, I know opposite. And let's say I wanted to find the adjacent side, right? So if I'm going to use the opposite, which is the side I know the angle, and I want the adjacent side, I'm going to use the tangent. Why? Because it has an O and an A in it, right? So I'm going to start by setting up the equation tangent of 42 degrees is equal to the ratio of 3 opposite over what I'm looking for, A adjacent, right? And so now my calculator is going to help me figure out what tangent of 42 is. That's just a number. It's about tangent of 45 degrees, which is 1. Sine over cosine, sine of 45, cosine of 45 the same. And so now I just need to isolate A. So to solve this equation for A, I'm going to multiply both sides by A. So the A comes out of the denominator here, pops up in the numerator here. And then I'm going to divide both sides by the tangent of 42. Right, I'm just isolating algebraically for A. Okay. And so now I'm going to turn to my calculator. Yep, solving right triangles. I'm going to clear that. And I'm going to make sure I'm in degree mode, right? Because this is a tangent of 42 degrees. So I need to press mode. Make sure I'm in degree mode, right? So I'm going to press enter. I'm going to quit it. And now I'm going to use my calculator. 3 divided by tangent of 42. And I don't even need that last parenthesis. I'll put it in there. Bada bing, bada boom. Right? Which is approximately, we'll call it, we're going to round to 3 decimals, the thousandth, 3.332. Okay? So what I just found is that this side length here is 3.332. Okay? Now right now we can find the hypotenuse in using several ways. One, we can use the Pythagorean theorem, 3.332 squared plus 3 squared equals 8 squared. Or 2, we can use some of our trig ratios. Okay? We can use this non-right angle or this complementary non-right angle, but never use the right angle as your reference angle. Okay? So you guys go ahead and find H right now. Pause. When you're done, unpause. Okay, now let's talk about how we can solve finding angles. Okay? So the way in which we can find angles, I'll just give you a specific problem and get right into it. Excuse me. Pardonnez-moi. Let's say that's a 3, 4, 5 right triangle. Right? And so what if I ask you to find the angles? So here's 3, here's 4, and by the Pythagorean theorem that has to be 5, right? So let's try to get both of the two complementary non-right angles of the triangle. So let's call that angle A, call that angle B, it doesn't really matter. Right? So to get A, I can use really any of the trig ratios because I know all 3 sides. So if I'm trying to find the angle A, it's my reference angle, then 3 would be my opposite side, 4 would be my adjacent side, and 5 would be my hypotenuse. So I'm going to choose just to use sine, right? So certainly it's true that the sine of that angle A is equal to the ratio of the opposite side, which is 3, over the hypotenuse, which is 5, right? Sine of that angle A is equal to the ratio of opposite, 3, over hypotenuse, 5. Right? So now, normally what we do to solve for a variable is we'd use the inverse operation to isolate. Right? So these sines, cosines, and tangent functions have inverse functions. And ironically, they're called inverse sine, inverse cosine, or inverse tangent. They're right here. See the second on your calculator, second sine, sine to the -1. That's called the inverse or arc sine. Second cosine is called cosine -1. It's called inverse or arc cosine. Here's my inverse or arc tangent, right? So what I'm going to do is I'm going to take the inverse sine of both sides. So it kind of looks like this. I'm going to take the inverse sine of, oops, I want that to be to the power Now it looks like it's to the power, but not really. It's just how we note the inverse sine, the arc sine. I'm going to take the inverse sine of the left side, which would be sine of A. And I'm going to take the inverse sine of the right side, which would be 3/5. Right? Okay? So that right here, this guy right here, that's called the arc sine or the inverse sine. It undoes the sine function. We'll talk about what it looks like and how it behaves at a later time. Okay. Now, because sine of the inverse sine, they're inverses, what that does is it just gives me A on the left. And my calculator is going to tell me what the inverse sine of 3/5 is. It's the angle A whose sine value is 3/5. Right? So on my calculator, I'm going to press second sine, arc sine, inverse sine of 3/5. So 3 divided by 5. I'm going to press enter. There's my angle in degrees. I'm in degree mode, so it's giving me the angle in degree mode. And that's going to be 0.86, we'll call it 870. Whoops, I don't know what I'm writing there, sorry. 36.870 degrees. Okay? So I just found, using SohCahToa, but this time finding the angle. Okay? And in order to do so, kind of set up the original equation as we would. You can use cosine. Cosine of A equals 4/5. Take the inverse cosine on both sides. Or tangent of A equals opposite 3 over adjacent 4. Take the inverse tangent on both sides. Okay? No matter which way you do it, you'll get the same thing. Okay? So that's how we can find angles. All right? We'll pick up with this tomorrow. Bye-bye.